So the next topic is Laplace transform of the integral of a function. Laplace transform of the integral of a function. Here, let Fs denote the transform of a function f of t, which is piecewise continuous. Piecewise continuous for t greater than or equal to 0 and satisfies a Groth restriction. That is, it is of the exponential order. Then for s greater than 0 and s greater than k and t greater than 0, comma, we have Laplace transform of integral from 0 to t f of tau d tau. This is equal to 1 by s, the Laplace transform of f of t. This is 1 by s f of s. Okay. So here the integration is from 0 to t, and this integration variable, it can be represented by any other symbol. Here I have used tau as the integration variable. Okay. So this is the Laplace transform of the integral of a function, and it is equal to 1 by s, the transform of the function. Okay. Then if I take the inverse Laplace transform of both sides, what do we get? Then taking the inverse Laplace transform, we get integration 0 to t f of tau d tau. This is equal to the inverse Laplace transform of 1 by s f of s. Okay. So let us use this particular formula to calculate some examples. So examples. Find the inverse Laplace transform of 1 by s square plus omega square, and the inverse Laplace transform of 1 by s square plus omega square. So first, let us find out the inverse Laplace transform of this. Okay. This particular expression, it can be written in this form: 1 by s f of s. So if I neglect this s for some time, then this particular expression 1 by s square plus omega square, it should be the Laplace transform of some function. And what kind of function is that? We know the inverse Laplace transform of, let us ignore this s once, then we have 1 by s square plus w square omega square. This is you multiply and divide by omega. Omega is a constant, So 1 by omega inverse Laplace transform of omega by s square plus omega s square. This is nothing but, this is the inverse Laplace transform of this is nothing but sine omega t. So this is 1 by omega sine omega t. Okay. So if I neglect this s, and when I consider this expression 1 by s square plus omega square, I find that the inverse Laplace transform of this is sine 1 by omega sine omega t. So now you compare this and this, you'll find that therefore inverse Laplace transform of 1 by s square plus omega square from this particular expression as well as from this expression, this is integral 0 to t sine omega t divided by omega, sorry, this should be tau, sine omega tau, because t is already an integration limit, sine omega tau d tau, and omega is a constant, like it can be taken outside. So this is nothing but 1 by omega square 1 minus cos omega tau t, and I put the limit 0 to t, you get 1 minus cos omega t. Okay. Now let me take another sheet of paper. Let us calculate the second part. Now Laplace inverse. Now Laplace inverse Laplace transform of inverse Laplace transform of 1 by s square plus omega square. This can be written as the inverse Laplace transform of 1 by s, then 1 by s times s square plus omega square. Okay. Now you compare again with this formula. Inverse Laplace transform of 1 by s, f of s. So inverse Laplace transform of 1 by s, this is f of s. And what is this? This is the Laplace transform of 1 by omega square 1 minus cos omega t. Okay. I repeat, what is this? This is the Laplace transform of 1 by omega square 1 minus cos omega t. Therefore, this should be equal to integration from 0 to t 1 by omega square 1 minus cos omega tau d tau. Okay. I got, because this is the Laplace transform of 1 by omega square 1 minus cos omega t dt. So that is integration of this from 0 to t. Okay, d tau. Now 1 by omega square, it is a constant, it can be taken outside. So this is 1 by omega square. This is tau minus sine omega tau divided by omega, and the limit 0 to t. This is nothing but t by omega square minus sine omega t by omega cube. Okay, so this is the required answer. These two problems can also be solved by using the method of partial fractions. Okay, I repeat, these two methods, these two can also be solved by the method of partial fractions. Okay, this is fine. I think that is all for today. I will stop here for today. I'll stop the recording.